In this video, we're going to talk about friction. And before I get into the details of why we observe what we observe, I want to give you two of the most fundamental properties of friction, because all the other stuff isn't necessary in terms of knowing what a friction force is in terms of solving a problem. You know, sometimes based on context, you know what the size of the force is, and that happens a lot, but you don't need to use the friction equation as such because we have a number for friction. So the two most fundamental properties of friction is, one, that it's always going to be parallel to the surface. And remember that this is the surfaces in contact. We looked at this whenever we defined the various forces that we would be working with. And so if you have a block which is at rest on a rough surface, that there are two forces due to, we'll call this the ground. There are two forces caused by the ground, is the way we define these forces. And the one force would be the normal force, which is perpendicular to the surface, and then the other was the friction force, which would be parallel to the surface in either direction, assuming that the box is sliding or something is pushing on it. So parallel to the surface is a fundamental property of friction that you have to know all the time. The other fundamental property of friction is that it's always opposing something. Okay, so for example, if this box were sliding to the right, if it had a velocity in that direction, then friction is opposing the slide. So it could be that it's opposing the sliding of the two surfaces which are in contact. Now, the other thing that friction could do is it may just oppose another force. Okay, but that force is attempting to make the object slide. All right, so for example, you know, it might be that this is a box which is sitting on the ground and you're just trying to push it towards the right, and so you apply a pushing force to the right. Now at this point in time, the box isn't actually sliding. You know, it's a very heavy box, and so you start pushing on it and you realize that, you know, by yourself you just can't push hard enough to make it slide. Well, in that case, the friction force does exist because you're pushing on it. Okay, now friction doesn't exist just because you have a rough surface. Okay, you know, for example, you're probably sitting at a desk or some other flat surface, and that flat surface probably has something on it. You know, maybe that something is just a glass of water. Okay, so that glass of water is sitting there. Now, we know that that glass of water is going to have a normal force which points up and a force of gravity which points down, and because this is a rough surface, you might be inclined to say that there's going to be a friction force which points either left or right. Okay, so if we were to draw an FBD that looks like this for your glass of water which is sitting on your tabletop, we have a problem. Can you identify what that problem is? If you said that the cup is in equilibrium, but the FBD indicates non-equilibrium, you would be absolutely correct. Because you see, the friction force is opposing something. It must be opposing something if it's going to exist. Otherwise, based on this FBD, your cup is going to start sliding without any apparent reason. So the only way that's going to happen is if this friction force exists, is if you actually push on it to the right. So this is not actually a possible scenario, you know, the way we've got this drawn. So you have to make sure that you're paying attention to the fact that friction will be opposing something, and that just because some of these other elements related to friction exist, like I said, for example, the surface roughness, that does not mean the friction force itself exists. It must be opposing another force if it's not sliding, and if it is sliding, then it's going to be opposing the slide. Okay, it's attempting to make the object slow down in most cases. Okay, so these are the two fundamental properties that we always have to keep in mind regardless of everything else that we're going to be talking about in this video. Now, there are two causes of friction, and the first cause is more of a macroscopic perspective. It has microscopic elements to it, please don't misunderstand, but macroscopically we tend to recognize friction as being caused by rough surfaces. And I really don't think I need to explain this one any further, because if you've ever been a child who was running and you tripped and you fell and you scraped your knee or you scraped your hand or something like that, then you're very aware of the effect a rough surface can have. Okay, so macroscopically we recognize friction as generally being due to a rough surface. Now, the second cause of friction is more of a microscopic perspective on friction. And microscopically, friction is also caused by cold welds. Now, a cold weld is literally whenever two surfaces touch, when they come into contact with each other, that the atoms and molecules bind themselves together at those contact points. Now, we have to be very careful in how we understand this, because microscopically the surface is anything but uniform. It is very, very rough, and there is actually very little contact. So, for example, it's approximately the area of contact, the actual area of contact, is approximately 1/10,000th of the measured area, the macroscopic area. So, if you have a 1 square meter object that's, sitting flat on the ground, then approximately a few square millimeters are actually in contact, and the rest is close but not touching. So a cold weld is literally a weld between the two surfaces, and it's something that is independent of surface roughness. These cold welds, they're going to exist whether the object is at rest or sliding. It really doesn't matter. The object can be at rest or it can be sliding. And the primary difference between at rest and sliding is that when it's at rest, you have more cold welds. All right, and whenever it's sliding, you have fewer. And that's in part because these welds have to form and break and form and break. And so, there's a lot going on microscopically, but the cold welds still exist, they're just fewer. Now, what this is going to mean for us in a few minutes is that when we look at friction, we have to determine, is this object moving or is this object not moving? Because if it's moving, that changes things. So let's just take a real quick look at, a surface microscopically. And I'm just going to draw some jagged lines because this represents a real surface. It's very random and rough. Okay, so there's one surface and here's the other surface. Okay, so the cold welds will exist anywhere the surfaces touch. And for our purposes, we could say that maybe it's touching here, and this might be close enough to be considered a touch, and that might be close enough to be considered a touch, and one more point right here. So we have actually very few touches going on. And you can also see how the surface roughness all the way to the microscopic level plays a part, because this is, like a jigsaw puzzle, and as these pieces attempt to slide past one another, they're going to be rubbing against each other, and that's going to, create that resistive force that we call friction. Now, the last thing I want to mention about cold welds is that a cold weld, you can some of you may recognize this through life experience. Whenever you try to slide an object, sometimes you'll hear a little snap. Okay, and that is sometimes going to be the result of those cold welds that are breaking. And certainly an example of where we see cold welds would be if you do any type of mechanic work and you've got nuts and bolts which are put together very tightly. If they've been sitting there for a long time, for sure, or they're very, very tight, sometimes you have to, what they say, crack the nut. Okay, and that just means you've got to get it started. And the reason that it's difficult to get it to start to go is because these cold welds have formed and you literally have to break these microscopic welds. Okay, so there's two other properties that we need to be aware of when it comes to friction. And the first one is that it's independent of surface area. All right, now this is on a macroscopic level. Okay, so what that means is this. If you have a brick, the brick is going to have one face which is rather large like this, and then there's going to be a smaller face that is much more narrow. Now, if we look at this on a microscopic level, we might find that there are 9 points of contact, or actually let's go with 8 points of contact. And we'll just say they're uniformly arranged like that. So there's our 8 points of contact. Now what happens whenever you place the brick over on its side? Well, when you place the brick on its side, those 8 points of contact get closer together. Like this. Okay, so they get all bunched up. And because it's, our friction is basically going to be caused by these touches and how much these surfaces rub past one another, we find that the area, the macroscopic area, has nothing to do with the friction force. So whether you have a brick on its large face or on its small face, it's not going to matter. The second property that we want to mention is that it's independent of speed. So how fast it's sliding has no effect on the size of the friction force. If it's sliding at 1 centimeter per second or if it's sliding at 20 centimeters per second, the amount of friction is going to be the same. Now, it's important that I add to this that this is, of course, within limits. All right, and as some non-examples or some counter-examples, this is what I mean by that. So if we look at the, well, actually, let's describe the limits this way first. The property of the material must not change. And here's what I mean by that. Let's suppose, for example, you replace the brakes on your bicycle with pieces of chocolate. So you use chocolate for bicycle brakes. Now, assuming that the chocolate doesn't crumble under the pressure of you squeezing on the brake, we still have another major problem with chocolate. And the problem is that chocolate has a low melting point, and as soon as you squeeze the handle for the brakes, the chocolate's going to get hot and it's going to melt. Well, that's a very different material once it's melted compared to when it's solid. So while it may have appeared that chocolate would be great for using as brakes because there seems to be a lot of friction associated with it, it's not going to work, okay, because we've actually changed the properties of the material. So that's a case where, it's not independent of speed, okay? Now, if we get away from the ridiculous of talking about using chocolate for brakes and talk about brakes on your car, okay, the exact same thing still happens. It's just it's much more difficult to make it happen. So if you've ever had the unfortunate experience of driving through the mountains and coming down a large hill, you have a vehicle which is heavily loaded. It could be your car. It could be a family vacation. There's 4 people in the car plus all this stuff for vacation. And you're coming down a really, really steep hill, and you have to put your foot on the brake to control how fast you're going down the hill, because you're still going to have twists and turns, and you have to do it safely. And so what oftentimes happens is your brakes will start to get hot. And for a while, that's okay. But eventually it reaches a point where the brakes start to feel mushy under your feet, and the stopping ability of the brakes is severely diminished. And what's happening there is that the brakes are getting so hot that you're creating a small layer of gas between the brake pads and the brake rotor on the car. And so you don't actually have the same kind of stopping surface anymore. And so that can be a very scary experience. But that's a case where, again, because the brakes got so hot, you created a gas in a place where there wasn't supposed to be a gas, and now the friction has actually changed as a result. So we always have to do things within limits. Okay, now, in terms of surface area, maybe we could talk about snow. And when you're driving in snow or on sand, it's always a good idea to have wide tires. But here's the thing. This is the important point about changing the property of the material. Snow, especially if it's a wet snow, if it becomes compacted, then it's no longer going to be the same amount of friction you would have had if the snow stayed more as a powder. All right, and the more you compact the snow, the more it actually becomes like ice, which is very difficult to drive on. And so most of you, I think, have at least some experience because of the recent snowstorms in January that we've had over the past few years. Most of you have experience with the roads becoming icy just because people are driving on the snow, and the snow starts to warm up a little bit, they drive on it, it gets packed really tight until it basically becomes ice, and then it becomes very slippery. So as long as you're not changing the property of the material because you've made the area so small, or because you're moving so fast and the heat generated from moving quickly with friction involved, as long as you're not changing the properties of the material itself, friction will be independent of area, and friction is going to be independent of speed. Now, we have 3 types of friction that I want to mention. The first type of friction is called static friction. And static friction simply means that you're not moving, or the object is not sliding. Okay, the object might be moving. For example, if you're in an airplane and you're walking along the floor, you're not sliding. I mean, you're moving at about 300 knots if you're at cruising altitude, but you're not sliding. Okay, so when we say static friction, we're talking about what's happening between the surfaces in contact, not what is the object doing. So that's a really important point. This is in reference to the surfaces in contact. Okay, so static friction, static means stationary, basically, means that the surfaces are not sliding past one another. It's going to point in a direction opposite the push of the other surface. So it points opposite the push from the other surface. Okay, now the equation, or our mathematical definition for static friction, is this. The force of friction is less than, force of friction static, is less than or equal to mu sub s times the normal force. What this basically means is that the friction force does not have to be equal to the maximum possible friction force. Okay, this less than or equals to. And what I mean is this, if by way of example, you have a, I don't know, maybe it's your glass of water still sitting on the desk, and you put your finger towards the bottom of that glass of water, and you very, very lightly give it a push. Okay, so you're pushing towards the right, very small force, but it doesn't slide. So what does that mean? The friction force points in the opposite direction, exactly the same size as the force you pushed with. If you push with a force which is a little bit greater, so now we're looking at that force, but the glass does not slide, then the friction force, the static friction force, is pointing exactly opposite of that, and it's going to be the same size. But eventually you push hard enough that the pushing force maybe is this large, and it does begin to slide. It just barely begins to slide. That is going to be our maximum static friction force, F sub S maximum. Okay, so oftentimes we are going to use the maximum friction force, but you cannot assume that you're always using the maximum friction force. And that's why we have this inequality. It's a less than or equal to mu sub S times the normal force. So if it's the maximum friction force, then we get the force of static friction is equal to mu sub S times the normal force. But remember that this is the limiting case. It is not necessarily true, so you have to pay attention to that. Now let's define what some of these variables are. You already know what the normal force is, so I don't need to describe that. Mu sub S is called the coefficient of friction, and the coefficient of friction is a unitless number, so there are no units associated with it. And basically it describes the stickiness of the surface, or I should say of the two surfaces which are in contact. The bigger the coefficient of friction is, the more friction that you have. The coefficient of friction can never be 0, but it can be quite small. So typical values for the coefficient of friction, and again, these are not absolute, but typical values would be going from 0.01 for an icy surface up to something which I'll say is approximately equal to 1. You can easily go beyond these limits. For example, if you have a tacky surface, then it's going to be greater than this. Okay, it's going to be much, much greater. And if you look at the joints in the human body, the synovial fluid that is in there reduces the friction between the cartilage that's coming into contact. It's reducing it down to something like 0.003. All right, so this is much, much smaller than the 0.01. So that's why I say, typical values, you're going to see 0.01 to approximately 1. You can easily go outside of that. And so I give you this range of values here so that whenever you're working a problem, you can, kind of gauge, is my answer reasonable or unreasonable? Now, the second type of friction that we're going to concern ourselves with is called kinetic friction. And kinetic friction exists whenever the two surfaces are sliding with respect to each other. And this force is going to point opposite the slide. The kinetic friction force is very similar to the static friction force. It's going to be F sub K is equal to mu sub K times the normal force. And again, the coefficient of friction, it's basically the same thing that we had before. It's just going to be a unitless number which describes the stickiness of the surface. Normal force, you know what that is. But if you're sliding, it's always an equal to, It's never an inequality. And that's because we are independent of speed. If we look up here, remember we took a note on that. Friction is independent of area and speed. So the kinetic friction force is not going to be determined by how fast it's moving, and that's why we don't see a velocity term show up in this equation. Now, there is a third type of friction that I want to mention, and we will not consider this type of friction in this course. Okay, and this friction force, and I'm going to do this in a different color, just so you know we're not going to be working with it, it's called rolling friction. And rolling friction is, it's a type of static friction, except rolling friction, well, you know, maybe a diagram here really would be in order. So let's say that we have a sphere. Maybe it's a bowling ball. Okay, so we've got a bowling ball. It's nice and heavy, and it's rolling across a hard surface. All right, now microscopically, that hard surface is still going to sag underneath the ball. We're still going to get this little dimple in the surface, because remember that atoms and molecules, you can almost treat them like they're connected by springs. So anytime you apply a force to the surface is going to give at least a little bit. Now, this ball is eventually going to stop rolling. We all have experienced that. We understand that a rolling object will eventually come to rest, and we know that that's going to be due to friction. So the question is why? You know, what's causing the ball to stop rolling? And you may be inclined to say that it's the front edge of the ball pushing downwards on the surface, causing the surface to squat or sag, and that takes energy, so it's going to take energy out of the ball, making it slow down. The only problem with that is that the surface is going to push up on the other side of the ball as it springs back to its original position. Because remember, it's like it's on springs, the surface, so it's going to return to its former state after the ball has passed over the top of it. Okay, so any slowdown that would have been incurred by the ball pushing downward on the surface here would be offset by the surface pushing back up on the ball on the other side. So actually I should probably fix my diagram here a little bit. And if we look at the forces acting on the ball itself, the surface here is pushing up on the ball, and the surface on the backside is also pushing up on the ball, the bowling ball, and we can see that the net torque on the ball is going to be 0 for the ball. So the ball should roll with a constant velocity based on this principle alone. However, the one thing that we haven't considered here yet is that anywhere the ball makes contact with the molecules of the surface, these two surfaces, we create these cold welds. And that's what's causing the ball to slow down. And so as the ball continues to roll forward, it has to break a bond here, and that takes energy. All right, and as the front of the ball rolls down onto the next piece of surface, it forms a bond. But then as the ball rolls back up, again, these welds on the back side, they're being broken, and that takes energy away from the ball. And that's why it eventually slows down. Now, rolling friction tends to be very small. And for all practical purposes in any experiments that we do, we're going to be able to ignore what the rolling friction is. And so that's why I bring it up, just so that you have a more complete understanding of friction. But it's not necessary for you to do anything with this information. It's more for your edification. It's just in there in the background. Now, the last thing I want to talk about is the friction equation and how that relates back to the surfaces coming into contact that we did earlier. Okay, so that we were looking at this, and we said that the friction force is going to be equal to mu times the normal force, generically speaking. Friction is equal to mu times the normal force. Now, why does the normal force increase the friction force? Look at this, take a moment and ponder it and see if you can figure out why the normal force is going to increase the friction force. Well, the short answer to that is that by increasing the normal force, you squeeze these two surfaces closer together, and when you squeeze those surfaces closer together, you create additional points of contact. So for example, this would easily become an additional point of contact. We probably would get one here and here, right? So I can add, a couple more points of contact. So effectively what's happening is on a microscopic level, I'm creating more cold welds, more points of contact. So by increasing the normal force, I increase the friction force because I've increased these contact points. So that's the idea behind it. In other words, you could think of it as the density of contact points increases as you increase the normal force.